Tonight we're building a neon-soaked Vaporwave 3D world from scratch in C++ and OpenGL, turning raw code into glowing horizons and endless grid lines. We'll take a blank OpenGL window, push it through the full graphics pipeline, shaders, geometry, camera, colour, until it becomes a retro-futuristic landscape. No Unity, no Unreal, just raw OpenGL calls and a bunch of C++. If you enjoy exploring low-level programming and retro machines, subscribe for more. And if you'd like to help support the channel, there's a Patreon in the description. This is not the 1980s. This weird multicoloured stuff that you see when you search 1980 is not what the 1980s were. I lived through it. The 1980s were not neon-soaked sunsets and synth music.
Hey everybody, an old man's talking.
This was the 1980s. It was dirty, cold, things kinda sucked. Bit like today, really. Sure, we aspired to this, but it's not how normal people lived. The closest we got was some rather funky colour schemes, a few iconic bits of hardware, and a hole in the ozone layer. But then the 90s came along and things improved. We had better hardware, better everything really. Computers that could do 3D. Okay, so the computers capable of doing 3D cost more than my car and weighed about the same. Maybe you've got one sat in your garage after buying it on eBay for 50p and you don't know what to do with it. So let's use some of that 90s optimism and make some pretty computer graphics, the likes that Pixar could only dream of at the time. So the aim is to make a scene with a camera that I can move around so I can explore what's going on. I've always wanted one of these proper 3D cameras, a bit like the Minecraft one where in creative mode you can just fly up and down left and right and go where you like. Because then I can have a floor, a bit of terrain and a pretty background. Now while I could do this in a 3D modeling program like Blender, because it's not really a game, I'm just trying to make a pretty scene, I'm trying to understand the techniques behind all of this. And there's a surprising amount of actual magic voodoo to make all of this work. So let's jump straight in at the deep end, get a basic cube on the screen and go from there. It's only mildly complicated. So what you might notice from just looking at the screen is that I've got quite a lot of files organised into different folders. As I've been writing this code, I've been organising it, trying to make it reusable. There's a lot of things in here that you don't need to know about at the moment, that as they become more interesting and relevant, you'll see them being used. This is how you set up an OpenGL context in C++. So I'm using SDL to initialize the video tool, and then I'm using this thing called GLAD, which is some sort of OpenGL. It's not a wrapper, it's a sort of, there's a lot of different ways of doing 3D on Linux. So you need something that sits between the video card and the OpenGL calls. And that's what this thing is. It's down here, this GLAD GL loader thing. So it binds a load of OpenGL function calls into what the video card actually understands. This editor, by the way, is Kate in Linux, and I've got the, not the ctags thing, I've got Clang running so that if it doesn't like a piece of code, it can tell me before it tries to compile it. So this is the basic way to get a thing open on the screen. There's some other stuff for the mouse and the inputs. There's an STL event loop, so I can go full screen and quit the program, otherwise it just crashes and you can't get out of it. So the part that we all came here for is how to draw a cube made from vertices. Here's how we build a unit cube. Now this one is a bit of a special one that draws the outline. We get to that later in the video. And you can see what it's doing is it just has all the vertices with also their colours and some other things like the UVs and some extra data. And it's just a list of numbers, then the indices. But it returns this thing called a mesh data. And all a mesh data is a C++ vector of floating point numbers for the vertices and a C++ vector of integers for the indices, and I can push that directly into the video card. I also need a camera. This is a class that represents a 3D camera, so I can get the field of view, I can get the position, I can work out the forward vector and the right vector. This camera is then just used by my code so that I can look wherever I want just by moving the mouse and pressing buttons on the keyboard. The next thing we need to look at is some shaders, because you can't make anything in OpenGL work if you don't have any shaders. This is not old school OpenGL where it just drew things with a fixed pipeline. But what even is a shader? Well, in modern GPU programming, where modern means things done in the past 20 years, it's possible and also necessary to give the GPU instructions on how to turn our triangles into images on the screen. Your GPU can do other things as well, like mine Bitcoin and generate AI content, because it turns out our GPUs just multiply numbers, and you can feed them grids of numbers and just tell it to work on them, which is what all these kind of calculations really are. So a shader is the code, probably the code because it shades in the texture, I assume, or shades in the screen and the triangles. But either way, the ones we care about are called vertex shaders and fragment shaders. And I've made a class to contain them, so we can switch out our shaders quite easily. So I have some shaders here. I've got a fragment shader and a vertex shader. The vertex shader is fairly simple. It just works out the world position of each point and passes that out. It works out the normal and passes that out as well. And then the color, and it works out the position of where the point is. The fragment shader does a little bit more. Some of this stuff here is for drawing the outline of the triangles that you'll see in a minute. But then also we've got to do some lighting. So this is like the weird thing about OpenGL. To see anything, you need lights. So imagine day one of OpenGL programming. You're still trying to work out how to get things into the video card. You've got a triangle, you just want to see it on the screen. Well, now you need to know about lighting calculations. And you need to be able to do them in a shader. So load a shader in out of a program and compile a shader. It gets really tricky really quick. So let's see this thing running and just see what all this code is doing. So here is classic OpenGL. There is absolutely nothing on the screen. It could have crashed. It could be that I'm just like not drawing anything in the right order. I could be drawing things but looking at them from the wrong side. Actually no, I just need to move the camera so I can see the object, and here it is. This is why getting this basic thing working was vital for the rest of this program. So I can look around the cube, I can go up and down it, I can do this. There it is, there's a cube. Okay, all that code just to draw a cube. So this is a fine starting point because I've got an object and a camera. This is the hello world of OpenGL. It's like leveling up from the previous video where I did all of this by hand. Now I've sort of worked out what's going on below the scenes, I can now build on top of it. Because now the GPU itself is calculating all the matrices. Now this might feel like I'm doing things the easy way, but I've merely just moved the difficulty up a level. I've gone from how do I plot pixels to how do I organize data in a way that the GPU can actually process efficiently. Because it's one thing being able to draw a single object and have a few matrices and a basic shader, but I want to build some sort of scene with more than one object. So things are about to get a lot more challenging. Before we even start loading objects, it's worth having a quick think about what an object even is. Like, you know, this is an object, but that's not what we're talking about. In 3D language, they're called meshes. And is that just the way the 3D thing looks, or is it the entire like entity in the game, or whatever you're talking about? We're kind of going for a bit of both, but mostly it's just meshes. And all meshes share the same basic concepts. They've got a list of vertices, and an order to join these vertices together to make triangles, but it matters what order you join them up in. And then there's other properties too, like their normals, which tell you which side is the front, and UV coordinates so that you know how to stick a texture to it or how to like color it in. Now in the things I'm showing you, I'm deliberately hiding some background code that's not relevant to this video. But here is what's required to load an object from a file and draw it on a screen. It's a random thing. I don't know why it says clock skew detected. Your build may be incomplete. I have no idea what's going on with that. Maybe my system's clock is wrong. 317, it says 320 on my clock. Maybe it is. Anyway, we'll ignore that problem because it seems to compile code anyway. Everything's made from triangles, but we need something a bit more interesting than a cube. Nobody cares about cubes. Let's load in an object. So you can see this code compared to the previous one doesn't look that much different, and that's kind of the point. I'm just getting the file names of all the different shaders and the object. Then I've got this thing called a shader and this thing called a solid color material. And then I'm loading in this object and then rendering it to the scene and putting it at a different position. The on update is always the same. So if we look at how we load in an object, so I'm using the tiny OBJ loader, which is this nice, really useful little single header file C++ library. And it will just load in a wavefront object file and then give me all the vertices and everything else. And then all I'm doing is sticking it into one of those mesh data structs from before, and I'm putting in the position, the normal, the UVs, and then my own color. And then this other stuff, ignore it. That's just for drawing the triangles. Future video mentions that. We'll get there later. And then I'm shoving in all the indices. So I load in the teapot, and I set a color for it. And if we run this piece of code, and bring it onto the screen, I'll make it full screen and get rid of it, we get this, which is very interesting, I'm sure. Shows that this is a complete model with the inside as well as the outside and a little hole there. But if I just clip out through it, there you go, there's a teapot. And I can circle strafe around the teapot. And you'll notice, unlike my handmade code from last time, if I clip too near it, the video card actually knows what to do, because, you know, it's a video card. It was designed for drawing this stuff. If we go back into the shader, you can see that the shader itself is doing the matrix multiplications. It occurred to me that this is what you're probably supposed to do. You're probably supposed to make the GPU multiply the projection, the view, and the world position matrices together by itself. I've seen in other OpenGL programming tutorials that you do this on the CPU and send it in as a uniform. But that seems a bit weird. You may as well just make the card do it, because the card is designed to literally do these multiplications. I guess the next thing is to look at how we make it look a bit more interesting. Okay, there's an element of flat shading going on and there's some lighting, so bits of it have a different brightness than others. But it's, you know, it kind of looks a bit boring. We need a texture on top of this thing. So what I need to do now is implement a bit more infrastructure. I know it's a bit like coding for coding's sake and making lots of different classes, and C++ can explode in a mess of files that just have like 3 lines in them. But actually it does make a lot of sense and it makes your code much better. And I need to introduce the concept of something called a material, which is my name for a class that combines a shader with a texture. Some materials just set values in the shader to control pixel colors. Others actually supply a bitmap, which represents an image to paste on top of whatever it is we're trying to draw on the screen that we've loaded into the GPU's RAM. Now, all of this sounds quite complex because it actually is, and there's no hiding this complexity. So it's one thing being able to colour things in. We need a texture though, otherwise we're just having like the whole same colour for everything. So again, I've just loaded in the teapot. I'm now loading in a test image that I'm going to use as the texture. So if we look at what that looks like, oh, we can't view them. Look, it's a PNG file. Interesting how it's got words inside it. There we go. So it's just pink. So it's just orange with the word test written on it. That's all we're having. Let's try and slap that onto the teapot. To do that, I have this thing called a file texture. Let's go look inside of that. So a file texture is a subclass of a thing called a texture. Let's just go dig through this little hierarchy of classes. So a texture has the OpenGL ID that is required with the video card, along with the width and the height, and this function called bind. And all that does is activates the texture and then binds it. So if we go back into the file texture, you can see that all we do is we generate a text using OpenGL. We set up all the parameters for whether it gets sampled and resized and everything. Then we use this STBI, which is that STB single file header image loading utility, which is also really useful. I like the way that people have made libraries that exist as single headers. So you don't need to install all this stuff just to read an image. You just need a header file you stick in your project. And then let's see what it looks like. Yeah, so that's not quite right. Something has clearly gone very wrong. This is the fun thing with graphics programming. Sometimes when it goes wrong, it goes really wrong. Wrong to the point of, like, you can actually see though that like it's trying to draw the texture whatever this is, you can make out parts of the word. So something is working. I'm loading in the image. It is sticking it onto geometry, just the geometry is a complete mess. Okay, this is looking more like it should do. Look at that. It says test on it. It's lit properly. It's not inside out. It doesn't look like some horrific, I don't know, crime against 3D programming. It's a teapot that's shaded and lit and textured. What I don't quite understand yet is how to texture the whole thing with one texture so that the top is different to the sides and different to the spout. I know that if I was doing something in Blender, I'd UV unwrap this and then draw on the image so that it wrapped it back around here. I'm fairly sure that's what I'd need to do to make this work, but I don't quite understand that idea yet. So for now, this is good enough. The text is the right way round as well. That was something interesting. I'll show you that. So inside the file texture, I have this bit where I flip vertically on load. If I don't do that, it appears upside down. In fact, not only does it appear upside down, but it appears back to front. You see? It's like I'm looking at the wrong side of the texture. This is just to do with where X and Y is and where the origin is compared to 2D image loading. So the fact that there is a specific command in the image loader to do that shows that this is clearly a thing that everybody has to do at some point. Our little 3D framework is starting to get useful, and it hasn't yet exploded into a tangle of code. We're doing well. Let's keep going. Let's get a floor. I want one of those weird, trippy Vaporwave neon floors with the lines across it and the grid and the neon and everything. That thing that I don't know where it came from, but everybody thinks it means 1980s. This is easier than it appears for once. In fact, from here things get easier in a way because I can build on what I've used, but they'll also get a little bit weird because we're doing some shader programming. All I need to draw on the screen is a pair of triangles to make a quad. And then they just need rotating and scaling to look like the floor, and then I just need to slap a texture on it. But the texturing won't use the same shader as before. I'm not going to supply a picture of a grid and just stick it down. It's not like I'm carpeting the floor with a pattern that's just grids. Instead, we're going to generate them inside the shader itself, which is a whole different aspect of weird voodoo that I barely understand, and I'm just starting to work out the basics. So let's go see what I can make it do. So the next part is we need a floor, that kind of grid going off into infinity purple box thing. You've seen it on 1,000 Vaporwave images. Don't know where it came from. But anyway, we need a quad. So I have a function called build unit quad. Let's look at that. It's really short. Here it is, build unit quad. We have some vertices. We've got its X, Y, and Z coordinates. And then some normals that all point the same way. And some UVs. And then I made it have colors just for some debugging earlier on when it wasn't working properly. And then the vertices, or indices even, to stick together the vertices. That's all it is. It's just a single quad that is 1 unit wide and 0 units tall. Which means if you look at it edge on, it doesn't exist. To draw it, we need to orient it the right way. This bit here, to be grid density and line thickness and line color, is to do with drawing the grid. So let's go look at how we do that. So, in a grid material, we have these floats and these vector 3s, and we're passing them in to the shader as uniforms. So we can set matrix for where it is on the screen, its projection, all that 3D stuff. Then we can pass in how many cells we want and how thick to draw them, what line color to draw them, and what to fill the boxes in that make up the grid. This all ends up going into the shader. So the vertex shader doesn't really do anything, it just works out the position and passes that on so that the video card knows where to draw things. It all happens in the fragment shader. So here's cells, thickness, line color, back color. That's these here. So that's how this is passed into the shader. And we're working out some maths to work out a grid, doing some confusing stuff with screen space and UV space, and I don't really understand this. I kind of chat GPT'd it, which I know feels like cheating, but I am trying to learn 6 things at once. If we see it running, the effect is actually pretty cool. So here we go. You can see that we've got the lines going off into the distance, and this is a different colour to the lines, and it kind of recedes. The illusion is totally broken if I move. Like, I can move around and you can see that this is actually just a big flat plane. So this is a nice ground that we can use in our little scene that we're trying to build up. So far I know how to load objects, and I've got the floor. The next thing to do is work out some mountains. I want little mountains to pop up in the background, just like here. And then later I want the sun. So let's go make the mountains appear. Now this is very nice, and not a single line drawing algorithm anywhere. How and why this works, as I kind of half rambled on before, I barely understand it, and I ChatGPT'd part of it just so I could make something work. It's a topic for another video. Although, there is this YouTube channel that doesn't seem to have posted in a while, which is a bit of a shame. He does a far better way of explaining how to draw things with shaders than I ever could do, and it's worth having a bit of a watch. I think my head's going to explode from trying to figure this stuff out, so let's carry on. Let's draw something different. Well, next on the list of cliched faux 80s aesthetic is some mountains, and I want to put them in the background. Now, to do that, I need another helper function to generate a triangle mesh, and then some code to generate a bunch of heights that look like mountains. Mountains are just a mesh, so we have another function that I've called build Vaporwave grid. And if we look inside the helper functions for this thing, right, here's a function that draws a Vaporwave grid. It takes a width and a depth and how big you want the grid to be. And I think it does it in UV space, not screen space. But all we're doing is we're making a 2D grid of however big. And then for each one, we're using a height function to work out the height of that particular point. And then working out normals so that we have flat shading. Each triangle, we calculate the normal, we put its vertices in, along with the normal data, the UVs, and this bit of data which will become apparent in a minute. And then we do the second triangle. So we're just making a quad out of two triangles, and that represents each part of the grid. The height function is really fairly simple, actually. We just have this function that makes a pyramid using some very simple maths. And then we work out one big peak, and then we have a couple of smaller ridges coming off it. So we're going to go for like a big pointy thing with little pointy things either side. So this is a mountain. This is exactly what we're looking for. Go up. You can see it's got a main pointy bit and then little pointy bits either side of it. And it generally looks sort of like the kind of thing that you'd see in the background of a 1980s 3D movie. Now, it's good, but it just needs one finishing touch. We need to see the triangles making up the mountain, not just its shape. And this is where modern GPU programming adds a layer of complexity already to what seems like a simple task. In my previous renderer, in my other video, I just drew out the triangle and then drew around the edges because I knew where the points were and I could draw lines between them. But this is a GPU. Its entire aim is to draw triangles where you can't see them, so you can draw tiny ones and make it look like smooth landscape or whatever you're trying to build. We've got to sort of defeat that a little bit. I can't just draw lines. There's no line drawing. So what I've got to do is figure out some weird maths and define a set of points and work out how to colour in the edges of the triangles. It's a complete thing. Here's what I managed to make it do. So I want to draw the outline of all the shapes, all the triangles that make up this mesh. I don't want to do that cheap thing where someone writes a shader that just draws a box shape over all the mountains, and you can see it's been stretched and warped as it fits the shape of the terrain. I actually want to outline every single triangle. Those of you that know anything about 3D programming and maths and have got a sharp eye might have spotted this word Barry and barycentric that's appeared in a few places. Let's just go and investigate that briefly. So when I upload data to the video card, one of the things I upload is called a barycentric attribute. It's a coordinate. What this is simply is a way of doing linear interpolation on an entire triangle so that no matter where you are inside the triangle, you can work out how far away from each point you are. And you can use that either to colour in the triangle to make it look that sort of triangular gradient fill that you see in 3D, or maybe it's the UV coordinate points from each corner to put the texture on properly, or I'm using it as a way to draw the outline. Let's get the shader open. So here's the shader. What it's effectively doing is working out the dot product for the diffuse lighting, but then it's working out where the edge is, and it's using these barycentric coordinates to work out from one point to another, where am I, and then from the other point, how far away from that line am I? And if I'm close enough to the edge of the triangle, I can fill it in a darker or lighter colour than the middle. So we're going for neon pink on the edge, and then whatever colour it is, I think it's green, for the middle bit. There we go, look at that. Ignore the green and red colour clash, I like that. But you can see each triangle has been outlined. And it's not just that I've drawn this sort of grid pattern across it wherever it fits, it is drawing every single triangle for me. And this is really nice, I like this. This is quite a cool effect. So I now have a background of a nice little mountain that I can stick in my scene. I can put the floor underneath it, stick the teapot on it. We now need a sun because it's not Vaporwave without a background. And this opened a whole massive mess. I think we're almost done. Just needs a few finishing touches and then it'll be perfect. The last part is a nice background. This is just done like the floor, sort of, with a quad and a shader. But the shader is really weird. I mean, all the shaders I've been showing you are a bit weird in the first place. The thing was designed just like texture stuff. Then people worked out they could generate the pixels as pictures, and then it all went bonkers from there. We're going to see weirder stuff. Like, I need to draw a background that, well, it's 3D, so where would you put it? Eventually you'd be able to walk through the sky, which would just look weird. So we're going to do some trickery with the matrices. Here's what I managed to make it do. Look at this amazement, it's a background. Yes, it looks like a shaded sort of gradient fill, but watch what happens when I move the mouse. You can see as I move up and down, the gradient changes. This is not because the brightness of the gradient is based on the mouse coordinates or anything weird like that. The shader is actually drawing this, and as I look up and down, it's kind of changing what I'm looking at. But there is a bit of a bug with it. I'm supposed to be able to see something as well. If I turn off the background without really explaining what's happening with it, but some of you can read words that are in the code, and you might be sort of getting an idea about what I'm trying to do. You can see that there's a box. That box should also be visible on the screen as well as the background, but it isn't. And it's because of the way I'm trying to draw any of this stuff. Let's just go look in the shader, because there's nothing special about any of this code. We're building a unit cube, we're running another shader, we've got this thing called Sky Cube, but really there's nothing special about this. If we're going to Sky Cube, which is in unit quad, okay, it is literally just a cube around the middle of the screen. Doesn't do anything special, it's just a cube. The shader though is a little bit special. The vertex shader doesn't have any translation in it. What I'm drawing doesn't move, and I'm working out the projection times this no translation thing, so it's just the view and the projection multiplied by the position. The fragment shader works out a gradient and mixes that and sets that as the fragment colour. So what exactly is going on with this? Well, let me show you the working version and then I'll explain it. Okay, so if I move, for a start there's this weird orange thing, but we'll ignore that. But look, there's a cube. So the cube exists. You'll notice as I move, the background doesn't get any bigger or smaller, so I'm not getting closer to it or further away. But I can rotate left, right, up and down to look at different parts of it. If I fly up and down, the sky doesn't change. So how is this working? Have I just put this massive quad behind everything that I'm now texturing with this image that I've generated? No. What's actually happening is there's a giant quad stuck in front of the screen, literally like as close to the screen as you can possibly get it without it clipping out of view. But then because I'm not using the position of this, I can force it in code to be behind everything and then cancel out any movement and translation that I do. So it's always in the same place, but I can still pass through any rotation like this. And it's all done using the shader. The actual code isn't any different, but it also slightly is, but not in a way that you might think. If we look in the shader, so this has evolved a bit. This involved some more ChatGPT because I really don't understand half of this bit. How to make a gradient and all that kind of stuff makes more sense now I've seen the code, but working out how to make it myself, I couldn't do it. Also, neither me nor it can figure out how to make the stripes on the sun. They just look shit, but never mind. But we've got some values we can change. So we work out a gradient sky, we work out which direction we're looking, and we make sure the sun is always in the same place. We try to do some strips which don't work, and we just combine it to make the one whole colour. Shaders are very interesting, how you don't draw pixel positions, you describe mathematically what should happen to each pixel on the screen, and that just builds up the image. The vertex shader does barely anything. Okay, this line here is what was wrong. So all we're doing is setting the Z position to be this W coordinate, which I don't quite understand what it is, and I'm sure a million people in the comments will tell me what it means, but I know that if I set the Z to the W, it always stays at the same distance no matter where I look, and it's always behind everything. Now, making this work did require a bit of like major surgery to my code. Like I had to have another whole set of stuff to do with my meshes. So I made it so that you could set attributes on a mesh. Otherwise, I had this sort of fixed set of steps that I went through to set up all the arrays, which meant they always had to have the same vertices and UVs and coordinates and everything in the same order, even if I wasn't using them. And this thing that says, is it a sky? Because it turns out you need a little bit of extra code when you're trying to draw this stuff. Inside the renderer, we work out what we're trying to draw. So here's my main draw loop. And the important bit is, we turn on the depth test, we clear the screen, then for all the objects in the scene, if it is the sky, we turn off the depth buffer, we allow the sky to exist, we render all the inside faces, and then we bind it and we draw it, and then we reset it back to normal. But I had to add this in, otherwise all I was doing is drawing everything, and you need to turn certain bits of OpenGL on and off to make this work properly. Shader programming like this is crazy. It really, really is. People write entire path tracing rendering programs in shaders. Originally it was just to colour in vertices nicely. Then they figured out that you could have clever maths that could actually draw images. So if you go on the Shader Toy website and look at what they're doing, you can see 3D objects moving around. But we're not sending triangles to the graphics card and having it draw those triangles. Instead, the triangles are part of the code, and they're manually drawing the triangles as a texture. I sort of get it, but only in the way that I can copy other people's ideas and make them work. Figuring out my own is just a whole different level of difficulty that I can't do yet. So go look at the Shader Toy website and look at the examples. They're awesome, but I don't know why they work. And here we are. I'm going to be quiet for a minute or so. I've done enough talking in this video, and I'm just going to let you experience the end result in all its neon glory. Well, that was actually pretty fun. I appear to have accidentally made a 3D engine. I wasn't planning on doing that, I was just going to fart around for a video, but then there's so much required to make a 3D scene that I thought I might as well do it properly, because now I can reuse it. I've got place for future content. A sort of like little universe that I can build things in. The terrain generation code I made was kind of functionally adequate, but a little bit rubbish, and I can do much better. One of my plans for the future is some sort of terrain generator where you can make a scene and then move around inside it and explore it. I was a bit conflicted about doing this relatively modern C++ and OpenGL stuff, but then I remembered that OpenGL is over 30 years old, and this newer-ish array-based OpenGL programming was introduced in the early 2000s, so it's pretty valid to be doing this. We're all supposed to be writing in Rust and using Vulkan now, aren't we? Not OpenGL and C++, but anyway. So follow me for more trailing edge techniques from 20 years ago. And if you feel like supporting the channel, my Patreon is in the link down in the description. I'm now trying to make more visually interesting things, so I'll be showing lots of demos and examples of what I get up to and sticking it on there because it's a nice place, free from any algorithms that might decide you don't need to see it next time you refresh your screen. In fact, on that note, if you got this far, press subscribe, because otherwise chances are this video or channel may never show up again if the wind changes in your preferred videos that YouTube likes to just feed you when you're watching it. So I'll see you later.